All right. In class, we looked at an example problem where we had a cord wrapped around a pulley. We were given some information about that pulley, mainly the fact that it had a diameter of 12 centimeters. We hung a weight from that and then allowed the weight to drop so that the cord unwrapped and the pulley turned. We could look at the fact that the pulley had a particular acceleration of 2.7 radians per second squared. And then we looked at finding the angular velocity after a certain amount of time, its angular position at that time, and then of course, based on all of the information from before, what distance does that weight travel as it drops. So we did that in class, and we looked at that initial position. We were able to assume that our initial angular position was 0 because no other information was given. We were told the fact that my angular velocity was 0, that angular acceleration was 2.7 radians per second squared. We had a time of 5 seconds, and then we first looked for our angular velocity. We were able to then identify an equation, plug in our numbers, and then come to a result. And then using that, we then moved on to our angular position, identify our zeros, plug in our information, and find an answer. We then looked at relating the arc length, right, or change in position sort of thing, to our angular change in position. So we did put those two together. It is important to note that we started with a diameter of 12 centimeters, but we're only interested in the radius, which is half of that length. So that's where that 6 centimeters comes from. And so we were able to plug in that angular position with our radius. We were able to get what that distance was. Moving on from this, we actually expanded this example a little bit further. Now we're given different sort of information. Now we're told what the final angular velocity is. We're told what the distance it travels is, but what is the angular acceleration? How do we get that information? Well, that brings us to sort of what piece of information do we know? Don't mind these. This is for a step that's going to show up in a moment. We know that final angular velocity. We know that distance it travels. We know its initial position. We know that it's starting from rest. Because it's the same pulley as before. Now we're hanging a different weight and just sort of shifting how we're looking at that problem. So this is actually the first place we need to begin. All right. In order to find anything about that angular acceleration, well, we need to know what our change in angular position is. Well, we're given linear, we need to move into angular. So we're going to do that sort of conversion. So we see the fact that in that drop, it moves 25 radians. All right. Knowing that information, we're then able to jump to this equation. All right. Note that we're using this one because we don't know how long it takes to drop. It's going to be a little bit different time than the previous one because we're looking at a sort of different information about the problem. So we have our final angular velocity. We know it starts from rest, so this term goes to 0. It starts at 0, and this is that final angular position, and we're looking for this angular acceleration. So we are able to solve that equation for the term that we want and then plug in our numbers and calculate and celebrate to get an angular acceleration of 1.28 radians per second squared. So we can wrap up that and sort of look at the same similar problem from a different side. The next thing that we're going on from this one is looking at the relationships between linear motion and rotating motion. In your linear and rotational mechanics analog table, you are going to need to put this in for your linking relationship for velocity. Your linear velocity is equal to your radius times your angular velocity. Because your linear velocity is going to change depending on how far from the center of that circle you are. I will tell you that this linear velocity is always tangent to the circular path. And you can also look at tangential acceleration. It's always, if I were to draw a circle, going on here, my circle is spinning, this velocity is tangent to the circle. We're also looking at an acceleration that would be tangent to that circle as well. This acceleration is actually going to cause the rotational speed to either increase or decrease. Our object is going to spin faster or slower because of a tangential acceleration. right? So this is your linking relationship for velocity. This is your linking relationship for acceleration. We can also look at the radial component of acceleration. Radial means actually along the radius, so it's directly towards the center or directly away from the center, so along the radius. You'll notice that this looks very, very similar to the centripetal acceleration. Because centripetal acceleration is directed towards the center, it is a radial component of acceleration. We then took this relationship here and plugged it into that equation to get this relationship. All right, we could go and look at the total linear relationship that includes what's going on, tangentially and radially. This can be a useful equation, but we won't really use it. We are more interested in what's going on individually, either tangentially or radially, not generally both at the same time. All right, so we're going to actually go ahead and look at another example problem. So we're looking at a weight attached to a pulley. Again, very, very similar to how we saw before. We have a cord. You can kind of see it wrapped around that pulley. And as this drops, this cord is going to come unraveled. And we're looking at that is going to drop a distance of 0.15 meters. We look that it completes a rotation of 2 radians. That means we're going to see theta naught is 0 and theta is going to be 2 radians. And we look at the fact that it hits the ground with a speed of 0.60 meters per second. If we're looking at meters per second, that is a linear speed. So that already tells us we're going to have to sort of engage in some more information. We're going to have to look at the linking relationships, that V is equal to R omega kind of stuff, to get a full picture of what's going on here. So we ultimately want to know how many revolutions per minute does this pulley complete. So I'm going to go to the next slide, which actually has the solutions, which I'm going to go through. So again, we look at the fact that its linear distance it moves is 0.15 meters. We are looking at the fact that it has a final position of 2 radians if our initial position was 0. It has a linear speed of 0.6 meters per second. And we want to know what is our angular speed in a particular unit. That means revolutions per minute. And then we're going to look at converting to revolutions per minute because our units aren't going to be that when we find our answer. As we move through this, we are going to look at, well, we kind of need to know the radius because remember, like I said before, the linking factor before was that V is equal to R omega. Well, we had this and we're looking for this, so we need this in the meantime. So that is where these 2 pieces sort of come into play to give us that linking relationship. From here, we're now able to rearrange this so that we have our angular speed. But remember, when we end up canceling this, we got meters per second over meters. Well, these meters cancel, and we're looking at rotational motions because we got rid of our length, our dimensional component here, that does get replaced with radians. So that we end up with radians per second here, right? Like I said, we're not interested in something in radians per second. We're interested in revolutions per minute. One of the big things we need to look at is the fact that when you complete a revolution, you're completing 1 full trip around the circle. Well, how big is 1 full trip around the circle? That's 2 pi radians. So we are going to go ahead and do a conversion for that. So 1 revolution is 2 pi radians. My radians end up canceling. We want revolutions per minute, so we need to convert from seconds to minutes. So I have both my conversion factors there. That does give me a final speed of 76.39 revolutions per minute. All right. I moved a little fast, but if you have any questions, let me know.